Cambridge Computer Science from the very beginning of the course. So we will be having a complete series of Cambridge Computer Science recorded in English. I hope you will find it useful for you. So I'm teaching the code 0478 or 0984. Both of them are exactly the same subject, exactly the same questions. However, with 0478, you may receive alphabetic grade. You will receive an alphabetic grade. So it is A star ABC. With 0984, you will be receiving a numeric grade. I think a numeric grade is better for a candidate. I think it is better because grade boundaries are a little bit lenient with 0984. Okay, okay, but both are the same. The same question comes in the two exams. The exact exam, only the cover that is different. Okay, so let us start with chapter 1, data representation. You should know that the computer only deals with ones and zeros. Okay, we will be talking about this now. So let us start the story from the very beginning. This is something called denary system, and these are the numbers that we deal with. Okay, so we are all familiar with the denary number system. Denary number system, you count 0, 1, 2, 3 up to 9. So you have 10 digits. You have the 0 and the 9. And also column weights. Column weights, this is weighted units, and this is tens, and this is hundreds, and this is 1,000 and 10,000. So column weights are multiples, or let us be accurate, column weights are powers of 10. Powers of 10. Okay, so we are all familiar with that. Denary. Denary reveals that is something about 10. DC is 10. Okay, so we are all familiar with the denary number system, which counts in multiples of 10. This gives us the well-known heading units and tens and hundreds and thousands and so on. A denary number system is a base 10. That's why we call it base 10, because we have column headings that are powers of 10. I will change this in powers. Oh, okay, powers of 10. Okay. Okay, so we also have the values from 0 to 9, and these are 10 shapes, 10 digits. Okay, that's why we call it base 10. A denary number system has units or column heading that increase by the power of 10. Okay, so here we can here approximately say count in units of 10, but however powers of 10 are more accurate, okay? So column headings would be 1, 10, 100, 1,000. Let us put it in a scientific way. So this is 10 to the power of 0. Anything to the power of 0 is 1. And this is 10 to the power of 1, and this 10 to the power of 2, and 10 to the power of 3, and 10 to the power of 4. Okay? This is the traditional, the conventional numbering system that we have always been using. Okay? Let me introduce another numbering system. That's going to be called binary numbering system. And binary comes from bi, and bi is 2. Okay? The point is, we are studying computer science, and the computer is all about ones and zeros. For some reasons, inside the computer, you only represent data in pulses or signals that can be only ones and zeros. Maybe you did electricity. Maybe you know about electricity. Computer is all electricity. Okay, maybe you know about switches, those electrical switches, maybe either on or off. There isn't a third position or a third status. Okay, so computers consist of transistors. Let us move to the computer world. Computer consists of transistor and logic circuits. We will be doing logic circuits in chapter 10. And it is very interesting, and it is very easy, not very, but it is easy to earn marks with logic gates that can only store and process data in two states, either high or low, either on or off, either 1 or 0. We only have two states, so we call this binary. Okay, okay, on the computer. So the computer uses the binary number system. Okay, all forms of data need to be converted to binary to be processed by a computer. Okay, that's why we call the binary number system base 2. So our binary number system is base 10. Our binary number system is base 2 because we only have two shapes. And the most important thing that column headings are powers of 2. Okay, so you have what is meant by column headings. I will be showing you now an example, and I will ask you to get a pencil and a piece of paper and redo everything that is written in my notes. Okay, so we have column headings that increase by the power of 2. Let us show it and then start using right away. So the first column is 2 to the power of 0. Okay, let us start with the scientific representation first. So the first column is 2 to the power of 0. Anything to the power of 0 is 1. And next is 2 to the power of 1. And next to the power of 2, to the power of 3, 4, 5, 6. Maybe I will show you how far we should go. Okay, however, let me highlight one point. You will go into computer science exams without a calculator. You are not allowed to use calculator. This is written on the cover of every exam up to the A level. Okay, okay. So I would like you to learn how to calculate things manually. Actually, they think that computer engineers do all the conversions and the calculations mentally because they are doing that over and over, and the subject is preparing you to be a computer scientist or a computer engineer. Okay, so 2 to the power of 0 is 1. 2 to the power of 2 is 2. Okay, please, you need to remember weights because they don't have a calculator to compute the powers. So column headings will be in that sequence. Eventually, you will memorize it. The column headings start with 1, and then the double of it is 2, the double of it is 4. So column headings are 1, 2, 4, 8, 16, 32, 64, up to 1 to 8 if you are dealing with 8 bits. And we call this a byte. If you have knowledge about computers, ICT, if you have knowledge about ICT, this is going to be most useful in my subject here. Because in the ICT, you know that a byte is 8 bits. From ICT, you know that computers only deal with ones and zeros. Okay, so that introduction would already be familiar for you. Okay, so column headings now become 1, 2, 4, 8, 16, 32, 64, 1 to 8. We stop now for the moment at 1 to 8 because this is a representation for 8 bits. Okay. A typical 8-bit binary number would be in the form of 1110, 1110. For example, this is just an example, okay? Okay, so that was the introduction. Let us now go to the conversion because definitely you will be having questions about converting from one numbering system into another numbering system, okay? So it is fairly straightforward to change a binary number into a denary number. Each time one appears in a column, the column value is added to the total. We will do examples right. Let's go directly into an example. The example says, we would like to find the 8-bit the denary equivalent of the 8-bit binary number 11101110. Okay, okay. So please, the method is very easy. Please put the weights. Weights start from the right because the right is the least significant bit. So put weights 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. And then underneath, put the value given in the exam or in the example. The value given here is 1110, 1110. Okay, so we will have something like this. We will have this. Okay? And now your duty is to multiply every column heading by the digit underneath. The digit underneath would only be a 0 or a 1. When it is multiplied by 0, it just goes away. When it is multiplied by 1, you just add column headings with ones underneath. So you are now have the duty of adding 128 plus 64 plus 32, and the 16 is gone because it is multiplied by 0. Plus 8 plus 4 plus 2, and the 1 is gone because it is multiplied by 0. The only challenge you need to do now is just to know how to calculate this manually. And I would like you from day one to start adding and subtracting manually, okay? Because there is no calculators in the finance. So you train yourself. So my advice is put 128 underneath, put 64 and put 32. I can do it like this. Let me show you how you are supposed to do it. So here you have 128. Please forgive me because I'm drawing with a mouse. Plus 64. You put this neatly, units and tens. It's not, yeah, these are now units and tens because we are dealing with degree. And then plus 32. And let us make things easier for us because 8 plus 2 is 10 plus 4 is 14. So all these, I will just write here 14. Okay, and then you have to learn how to add columns. So 8 plus 2 is 10, plus 4 plus 4 is 18. You put here 8 and carry the 1. Okay, so 6 plus 4, that's 10, plus 3, that is 13. Okay, put here 3 and carry the 1. 1 plus 1 is 2. So you are supposed to reach the answer 230. Okay, excellent. Now you have done that yourself. You are ready to do other calculations. Okay? Okay, that was an example about converting 8 bits, an 8-bit binary digit. If it happens, and this is the calculation, okay, okay. If it happens that you only have 4 bits, that's going to be very easy because weights are only now 1, 2, 4, 8. Sometimes we will be dealing with that thoroughly. Plenty of times we will be dealing with 4 bits in converting into something that's going to be called hexadecimal. Later, not now. Later, not now. So let us follow this example. This example is going to be very easy. Why? Because you have only 4 bits. If you put weights 1, 2, 4, 8, and you multiply them all by 0, the answer would be 0. The second digit would be 0, 0, 0, 1, and you put weights 1, 2, 4, 8, and it's going to be 8, and this is 8. The third digit, 1, 2, 4, so 1 plus 2 is 3, and this is 3. The fourth digit is 0, 1. I always read it from the left. I always read a number from the left. However, I put weights from the right because on the right is the least significant bit. So I put 1, 2, 4, 8. So it is 4 plus 1, and it is 5. When you come to 4 bits, you have to do that mentally or orally. You don't need to write it down. And this is what you're supposed to be doing. Okay, so now we did an example about converting an 8-bit, and that was not very difficult. And then the converting 4 bits, and that's very easy. Okay, what about if you get 12-bit binary? Okay, let me first teach you how weights will become when you deal with 12 bits binary. It is the same. It is the same. 1, 2, 4, 8, 16, 32, 64, 1 to 8. They are the same because here you are only up to 8 bits. Further on, the double, because every column is the double of the one to the right of it. Okay, so the double of 128 is 256. The double of 256 is 512. The double of 512 is 1024. And double of 1024 is 2048. Actually, these are to the power of 10, to the power of 2, to the power of 10, to the power of 11, and so on. But we don't need to remember powers, at least for the moment. Okay? So please give yourself time and compute this manually. So in that example, you need to add 1024 plus 512. You skip to 256 because it has a 0, plus 128 plus 64 plus 4 plus 2 plus 1. And you need to do that manually. The total is 1735. Okay? If you need to deal with 10 bits, if you need to deal with 10 bits, column headings will be like that. If you need to deal with 10 bits, column headings will be like that. 1, 2, 4, 8, 16, 32, 64, 1 to 8, and then this is 8 bits, and with for 10 bits, you also need to include 256 and 512. Okay. You are very clever. Please go ahead and compute those three binary numbers one by one, and I will reveal the answer as soon as you do it manually. Okay, please go ahead. Let us now look at the answers. So 000, 100, 110, it is written like this. You add 64, 16 plus 8 plus 4 plus 2, and it is 78. Okay, same for that pattern, 439. Same for that pattern. That the last pattern is very easy because it is 1 here, 512, plus 1 there, plus 1, that is 530. However, the point is, this is a very recent question. Now, in past paper, they don't give you lots of time to do conversion. They give you a bunch of 3 numbers to convert them all together. I think every one of them is worth 1 mark. So we have to learn how to do it fast and how to do it accurately. Okay? Okay, excellent. Now we have practiced about converting from a binary number into a denary number. What if we would like to do the opposite? Okay, you start with a denary number, and you would like to find ones and zeros that represent this number in binary. Okay, it is very simple. It is just however, it is the same thing. However, the same column weights. However, I probably you will be doing subtraction instead of doing addition. Okay, let us study it by example. Okay, the method involves placing ones in the appropriate positions so that the total equates to the given denary. The weights for 8-bit weights are the same. If you are dealing with 8 bits, if you are doing with 4 bits, if you are doing with 10 bits, 12 bits, the same weights are there. However, the process will be the reverse. Okay, so weights for 8 bits is like that: 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. Weights for 12 bits is like that: 1, 2, 4, 8, up to 2048. And you should memorize this. Actually, you will memorizing by practicing. Okay, and every column weight is double or twice the one to the right of it. Okay, okay. So and in the exam, I think they will mention to you convert it into 8 bits or convert into 12 bits, because soon this is going to be very important. Okay, let me give you two examples, the two easy ones, and I leave you with other examples. The difficulty is about the value of the number. Okay, so let us convert the binary number 57 to 8-bit binary number. Okay, you put the weights, and now, up till now, you don't know where you put ones and zeros. There is a systematic way for finding the correct ones and zeros directly. Okay, so you have 57. If you consider putting a 1 under the 128 column, you say, no, I cannot afford to put a 1 here, because if I put a 1 here, this will add 128. And I only have 57. So please put 0 under the 120. Okay. Definitely, you need every time to start considering from the left. Okay. So you put 0 under the 120. And then you consider the 64, you put 0 under the 64, because all what you have is 57. 32, you can afford putting 1 under 32, and you must put 1 under 32. However, when you put 1 under 32, you subtract. You subtract 32 from 57. So after putting a 1 here, you are left with 25. Now you have 25. Consider the 16. Yes, you must put 1 under 16. And then subtract. So 25 minus 16 becomes 9. You must put 1 under the 8 and subtract. You are only left with 1, and you put the 1 here. Actually, when I come to the last 4 bits, I just can easily recognize the pattern. Okay, so the 9 is 1001 because it's 8 plus 1. Okay, this method is systematic, and it will always take you to the correct answer. Okay, as long as you start from the left and you find weights that you can afford to put ones underneath, and if you put 1, you subtract and think how to find ones for the remaining value. Okay, let us do another example. Okay, and then let me give you examples, you do it yourself. Okay, so to represent 57, it's gonna be like this. And if you do the reverse, like adding 32 and 16 plus 8 plus 1, it will equate to 57. Okay, okay, let us do another example. I have 107. Okay, so again, you start from, you put the weights. First, you put weights, because the exam is asking you to represent 107 in 8 bits, because zeros on the left, they must be written. Okay, because the exam is saying 8 bits. If you omit them, maybe you don't get them all. Okay, so I have to represent 107 in 8 bits. Okay, weights are 1, 2, 4, 8, 16, 32, 64, 1, 2. Okay, I cannot afford to put 1 under the 1 to 8. Why? Because I only have 107. So put 0 underneath. The 64, you must put a 1 under the 64 and subtract. Okay, so this is the whole story written here. The whole story is written in my notes. Okay, we put 1 in, under the 64 and we subtract. Okay, and then we get 43. We put 1 under the weight 32 and we subtract, and so on and so on and so on. Okay, okay, so if you follow these, okay, you get 0, 1, 1, 0, 1, 0, 1, 1. Okay, okay. So these are the two examples I am representing for you. Okay, next. The exam is asking you. Please notice here because we have something different. The exam is asking you to represent 300 in 12 bits. Actually, later on, I will tell you that 300 can never fit in 8 bits. Okay? Okay, so please put the weights and please do it yourself. Okay, okay. Now you put one under, you cannot afford to put a one here, you cannot afford to put a one here, you cannot 512. You fill 3 zeros, and those 3 zeros must show in the exam because the exam is asking you to use 12 bits. So you have to fill them with zeros. And then 256, 300 minus 256, you remember the remainder is 44. So you look at that, you only have 44 right now. You cannot afford here, you cannot afford here. You only have 44, so you must put a 1 under the 32 weight. And you subtract, okay? Now subtracting, you get 12. You cannot afford the 16. You put 1 under the 8 and 1 under the 4, and that's it. Okay? Okay? Okay, so next, let me give you even a bigger number. Okay? So please, the next example is say, convert the following denary 431 into 12 bit. Actually, anything, we will come to that point. Anything that is greater than 255 cannot fit in 8 bits. There is a special question about that, the number of bits necessary for a value, for a given value. Okay, and typically up above the 8-bit is 12 bits. Okay, so the exam is asking you to convert 431 into 12 bits binary. Okay, please go ahead. Okay, let us go through it. So you have to fill all these with zeros because you have 421. You start with 256 and subtract. And then you have 175. You put one here and subtract. You have 47. Then you put here 0. You put under the 31 and subtract. You have 15. And when it comes, actually, because of something that is going to be called hexadecimal that always deals with 4 bits, I just patterns, 4-bit patterns, I just know them very well. When I have 15, I start fill them all here with 1 plus 8, because 8 plus 4 plus 2 plus 1 is 15. Getting experience and practicing will help you a lot in the. Okay, so this is the pattern you are supposed to have for 0, 4, 3. Okay, okay, let us move on. Another example, 2640. I think this is the last example I have. So difficulty only depends on the value of the number. Okay, please. And it 256, 2640 must be represented in 12 bits. Go ahead. Okay. So the same thing. There is sometimes the pattern looks nice because when you have 2640 and put one here, you subtract 2640 and you subtract minus 2048, and the remainder is 592, and this goes as 0. 592, you put one here and subtract, and you get 80. So you fill here 0 and 0. You put one under the 64, you put one under the 64 and get the remainder is 16. You put 1 under the 16 and the rest is 0, and that is so easy. Let us now discuss another point, the maximum value. What do you think would be the biggest denary number that may fit in 8 bits binary register? A register is something we are going to study. A register is just like a storage location. So actually you have now 8 bits. We are just introducing the word register. Yeah, it's okay. You're going to be dealing with it quite often. Okay, so I would like you to find the biggest value, the largest denary value that can be stored in an 8-bit binary register. Okay? Okay, you go and fill it all with ones. Go and fill it all with ones. Okay? And find this out yourself. Please add them and tell me the answer. Okay, thank you very much. Doing it yourself, it becomes 255. Okay? Okay. Let me tell you about, sometimes I get ideas from students that are really helpful because students would like to do it the easiest way. So the easiest way to do it, if you have 8 bits and here you have 128, twice of it is 256, subtract 1, it's going to be 250. Okay, I learned that from a student because students would like to find an easy way of doing this. Okay, so get brilliant ideas. Okay, so if you have 8 bits, on the far left, the leftmost weight is 128, twice of it, 256, subtract 1. I will tell you in a moment that that 1 is subtraction of 1 is really a rule. It's a rule, okay? And it is 255. You did that yourself, and you found that the total is 250. Okay, that's good. There is an official way of calculating it besides that student idea way, which is very brilliant. We can calculate the maximum value from the formula 2 to the power of n minus 1. And that formula will be used extensively in the AS. Okay, I'm trying to prepare you for the AS from now, if you wish. So we have 8 bits. 2 to the power of 8 is 256. I would love if you memorize powers of 2. And later on, with hexadecimal, I'll ask you to memorize multiples of 16. Not powers of 16 because it's very complex, just multiples of 16. Okay? So 2 to the power of 8, especially 2 to the power of 8, because popularly, quite often, you will be dealing with 8 bits. Okay? So 2 to the power of 8 is 256 minus 1. This is the rule. I can tell you why, because you're starting from 0. I can tell you why you need to subtract 1. So it is 2 to the power of n minus 1. 2 to the power of n, I just know it very well. It is 256. Minus 1, it is 250. Okay? Okay. Next, what about the largest denary value that could be stored in 12-bit binary register? I will not ask you to add all these ones. If you add all these ones, if you like to do it, you may pause the video and add all these ones. If you add all these ones, you will get the value 4,095. Okay? Let us apply the rule. Let us apply the rule and try to remember powers of 2. Try to remember powers of 2. We can calculate the maximum value from the rule, from the formula. From the formula 2 to the power of n, and n here is 16. To the power of n minus, I'm sorry, n here is 12. To the power of n minus 1. So 2 to the power of 12 is 4,096. Or you can just say twice of this and subtract 1. Okay, 2 to the power of 12 is 4096, which is twice of this, minus 1. So the largest value that may go into 12 bits is 4090. You can add these yourself if you like to prove it. Okay, why do I need to tell all these? These are used extensively in the AS, but we are here in the O level. Once I saw that question, and then I said, let us teach it. The question was saying, what is the least number of bits that can be used to store the denary number 301? We already know that if you use 8 bits, the maximum number that can be stored in 8 bits is 255. So 8 bits will not be enough. Please, now you try 9 bits, 2 to the power of 9, okay, minus 1, and tell me if 9 bits is going to be enough, because I want the least number. Don't you go and just put it in 12 bits or 16 bits. It's going to be work, but it's going to be waste of storage. I just want the least number of bits that can accommodate 301. Please, please do it yourself. Try 2 to the power of 9 minus 1, to the power of 10 minus 1, okay, and tell me how can you do it. Okay, so we can try 8 bits. 2 to the power of 8 minus 1 is 255, and this is not enough. We can try, we try 9 bits. To the power of 9 is 512, minus 1 is 511. Okay, so the smallest number of bits that can be used to store the denary value 301 is 9 bits. Okay, let us try another example. And actually, you have to trust me. I am copying all these from past papers. So everything in here has shown in O-level past papers. Okay? Okay, let us do that next one. The smallest number of bits that can be used to store the denary value, 2000. Okay, please go and try. Definitely the 9 is not enough. Maybe the 10 or maybe the 11. And don't exceed, because we know that we want the least number of bits. Okay? Yes. We can try the 9. 2 to the power of 9 minus 1 is 511. We can try the 10 to the power of 10. I know very well the 2 to the power of 10. Okay? Okay. 2, because the kibi, we will be talking about kilo and kibi. Okay? 2 to the power of 10 is 1024 minus 1, 1023. So 10 bits are not enough. We try 11 bits. To the power of 11, 2047, 2048 minus 1, 2047. So the smallest number of bits that can be used to store the denary value 2000 is 11 bits. If you say 12, will not be awarded a mark, because 11 is enough. Okay? Excellent. Let us study another topic, a very easy one. Logical binary shift. You have a pattern of ones and zeros. What if you shift them all one place to the right? Or what if you shift them all one place to the left? How that can be done? Maybe they ask you to do this. And what is the effect of doing that? I will teach you the effect. We will practice. We will practice. Okay? Logical binary shift. Let us read the definition, because I would like you to do it exactly as defined. It is very simple. I just want to warn you about one little thing. In logical binary shift, bits shifted from the end. So some bits will be here. Bits. This is shift to right. This one goes in here. This one goes in here. This one goes in here. This one goes where it is lost. Here you will have an empty place. You fill it with 0. Not because you lost here 0, you fill here 0. No. Whatever is lost from one end will be lost. Okay, if it is a 1, if it's a 0, it just goes. Okay, and you fill on the other side with zeros. Don't think of cycling this and putting it here. Then this is another definition. I want logical binary shift. The other one is cyclic or something, not the one defined in our section. Okay, so bits shifted from the end of the register are lost, and zeros are shifted in at the opposite position. Okay, the number. Okay, what is the effect of shifting? Let us learn it by this example. Okay, and I would like you to do it yourself. I would like you to do it yourself. Actually, that was in an exam. They give you that pattern 0, 1, 1, 1, 0, 0, 0, 0. And they asked you to shift it one place to the right. So shifting it one place to the right will be like this. And that question was a little bit old. At that time, they were very kind that they put weights for you. Nowadays, no way. You put weights yourself. Okay, I'm asking you a very little task. Please convert this pattern before shifting into binary and convert that other pattern into binary after shifting and compare the two values. So the value before shifting is 112. The value after shifting is 56. If you compare the two values, you will find that the 56 is exactly half of the 112. Okay, so the effect of shifting a binary pattern one place to the right is about halving the value. And it is quite obvious, I can tell you why. Because whatever used to be the one under the 64 is now under the 32. The one under the 32 is now under the 16. The one under the 16 is one under the 8. Is all shifted one place to the right, and everything is halved. We can also assume that shifting to the right is doubling. Okay, so please read this because this is what I should have been teaching, but you just discovered it. Okay, so shifting one place to the right has the effect of dividing by 2. Shifting one place to the left has the effect of multiplying by 2. Okay, so also you have to study about shifting. Okay, let us go to another topic. See, we have plenty of topics. Okay, let us go to another topic. What do you think? Can you add and subtract numbers? No, you don't need to subtract. Subtraction is in the AS. Okay, can you add numbers in binary? Let us read about it and let us practice it. Okay, the addition of two 8 positive binary numbers. We are not yet talking about negative numbers. Hopefully, subtraction will not be in that. Definitely, inshallah, subtraction is not in your O-level syllabus, but it is there in the AS. So just get prepared. Just get prepared. Okay, the addition of two 8-bit positive binary numbers. Okay, the following key facts when carrying out addition of two binary numbers. If you add 0 to 0, the result will be 0. If you add 0 to 1, the result will be 1. If you add 1 plus 0, the result will be 1. However, if you add 1 plus 1, the result is 2, and you cannot represent 2 in binary. It's going to be 0 and carry 1. The same principle of carrying when adding binary numbers, but when in binary, when a number is above 10, you do carry. Here, when it is just above 2, you do a carry. Okay. Let us extend, because when you have a carry, you will be adding 3 numbers. So 0 plus 0 plus 0 is 0 and no carry. Okay, 0 plus 0 plus 1 is 1 and no carry. Okay, The only different thing is that 1 plus 1, here 1 plus 1 plus 0 is 0 and carry 1. The last thing, 1 plus 1 plus 1 is 1 and carry 1. Okay? We will understand it by examples. Okay? We have to look at examples and then we can understand it. Maybe this should be the last thing we do today, and then spend the rest of the time doing classification. Okay? So let me do this working example. It is copied from the textbook, Huder textbook, with all colors and all explanation. It is really, really helpful. Okay, let me go through it with you. So the question asked to add this to that. You have to perfectly align them. Okay, you have to write 0, 0, 1, 0, 0, 1, 1, 1. This, you have to write it here. And the other one perfectly underneath, clearly, because I don't want to get confused. Okay, let us start adding. 1 plus 0 is just 1. Okay, okay. Remember the things we taught here. Okay, however, 1 plus 1 is 2. You cannot write 2. 2 is 1, 0. 2 is 1 represented in binary as 1, 0. So 1 plus 1 is 0 and carry 1. Okay, now here is 1 plus 0 plus 1, because that one carried will be added. Okay, so 1 plus 0 plus 1 is again 0 and carry 1. And here 0 plus 1 plus 1 is 2, but we present 0 and carry 1. And then 0 plus 0 plus 1, okay, this is 1. And then 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. So the answer is 0, 1, 1, 0, 0, 0, 1. Okay? If you'd like to practice, you may convert this into denary, convert that into denary, and also convert the sum into denary, and they will find that it is added. But please, in the exam, do not do that, because they will ask you to show your working, and they would like to see that you successfully added numbers in binary. Okay? Okay. Can you do this yourself? Can you do this? There is also a thing called overflow error. Let us keep it for a moment. Please add these yourself. Okay. So 0 plus 0 is 0. 1 plus 1 is 0 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 0 plus 1 plus 1 is 0 and carry 1. 1 plus 0 plus 1 is 0 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 0 plus 1 plus 1 is 0 and carry 1. Let us discuss this. The last carry is requiring you to use a 9th bit. Okay, if you get this in the exam, just put it in. However, they will ask you that this would result in an error. If you have only 8-bit registers and you need a 9th bit, this will flag what is called overflow error. And this is the thing that I should have taught you before, but I just wanted you to discover it yourself. Let us interpret this. Let us interpret what is happening. Because we know that the biggest number that can fit in 8 bits is 255. So maybe that number is within 255. That other number is within 255. However, when you add them together, maybe the result is something above 255 that needs 9 bits. If you can have a 9th bits, that's okay. If your system is only limited to 8 bits, we are going to call this overflow error. Okay? Let us read the definition for it, because you just practice it before we teach it, but it's okay. A computer or a device has a predefined limit that it can represent or store. For example, 8 bits. An overflow error occurs when a value outside this limit should be returned. An overall error will occur if the result of summation is greater than 255 in an 8-bit register. Okay? That's why they will ask you about that 9th bit and what error does that represent. At that time, if they ask you, at that time, you should say that this is an overflow error. Okay? Let us stop for here. We cannot take any further. Let us stop for here and go to the classified and solve from it as much as possible. Let us go now to my classified past paper. We are covering from March 2018 till March 2023. You know that there has been a syllabus change in 2023. So my classified is adapted to the new syllabus, omitting old topics that are no longer, and also adding, maybe I used to add exercises from the AS. Maybe I am adding exercises from the ICT to cover, because now we are in the transitional period where we don't have plenty of examples post paper. But very soon, after one session or another, I will have plenty of exercises, and I don't need to put AS examples anymore. Okay? So let us go to classified chapter 1, data representation. Let us go to the first question, and let me show you how to get to mark schemes, because I have written here that this question is taken from 20 March paper 1-2. So if you go to that folder with past papers and mark scheme, I'm offering you a free download for the mark schemes from my Google Drive. Okay, you go, for example, into 22 March, and this is 22 March, paper 1-2 MS, question number 5, and this is the answer. The question says, programmers can use denary and hexadecimal. I didn't teach you hexadecimal yet. Okay, these values are stored in a computer system using binary. Computer can only store binary. The question says, explain why binary is used to store data in a computer system. You cannot say because computer can only deal with ones and zeros. I want to know why the computer can only deal with ones and zeros. Okay, the answer is computers, they don't put any grammar in the mark scheme, so just don't mind. Computer consists of transistors. Just don't mind about the grammar. These are not model answers. These are keywords for examiners to award marks. I'm just making use of it and teaching it to my students. So the computer consists of transistors and logic circuits that only store or process data in two states, as high or low, on or off, 1 or 0, and that's why the computer can only deal with binary numbers. Please copy this. Okay, let us go to next page. This question is taken from 22 June, paper 1-2. You know now how to get to the mark scheme. The question says, denary values are converted to binary values to be processed by a computer. Okay, draw one line from each denary value to the correctly converted 8-bit binary value. It's up to you to convert 41 into binary, convert 174 into binary, 86 into binary, and then match. Give yourself some time. Let us check the answer. So 41 goes into that. 174 goes into that. 85 goes into that. It would have been easier to convert from denary to binary, but you have then more numbers to convert, and you only have 3 denary numbers to connect to. Okay. You may use this area for your work. Binary values can also be converted to denary. Now we are asking you to do the same, the opposite. Give the correct denary value for the 12-bit binary. Now it is 12, so you have to put weights 1, 2, 4, 8, 16, 32, 64, 128. What's else? 256, 512, 1024, 2048. Okay? And show your working and give the denary value, and it is worth 2 marks.